Air pollution is a silent killer. Like many issues in environmental health, the way that air pollution affects us is not always obvious. It takes some detective work to figure out what is going on in our body and to attribute it to the contaminants that are present in the atmosphere. In this video, we're going to actually talk through how air pollution enters our body, what it does when it gets there, why does it affect our cardiovascular system, and we'll also talk about the methods that are used to sort of pull apart all of these effects. This is one of the most serious environmental human health issues that we talk about in environmental science. So hopefully by the end of the video, you'll know more about this topic. We'll start by talking about how we actually know what air pollution does to the body. This is a very complicated area of research that involves both pathophysiology and epidemiology. We'll look at some of the major physiological impacts of pollutants that are regulated under the Clean Air Act, basically trying to gain a better understanding of what actually happens in your body when you're exposed to air pollution. Then we'll finish up by looking at how the cumulative long-term exposure of air pollution affects morbidity and mortality, both internationally and domestically. Virtually all air pollution impacts on health start with the lungs. The lungs are where the exchange of oxygen and CO2 occurs. And we know a fair bit about how air pollution actually affects the physiology of these processes. But to understand this, it's really helpful to first start with a little bit about how the lungs work and the structures that are impacted by air pollution. So if we start here at the top of this picture, we see the larynx, which is about where your voice box is, and then the trachea, where air flows down from your nose and mouth to your lungs. The physiology of the lungs basically goes from large tubes like the trachea to tiny tubes, eventually in the alveoli. Basically, the trachea branches to the bronchi, which branch to smaller tubes called the bronchioles, and then finally these little tiny sacs called the alveoli where oxygen and CO2 are exchanged with the pulmonary veins and the pulmonary arteries. Air pollution travels with the air that flows into your lungs, and depending on the size of the particle and its chemical properties, it will end up in these tiny sensitive tissues where gas exchange occurs. We worry about small particles because they go farther into our lung tissues. In a big picture sense, this is where the problems with air pollution start. Because you can absorb toxic metals at this location, there can be physical reactions and particularly inflammation that occurs as a result of contaminants reaching these points in your lungs. And many air pollutants can cause problems with oxygen exchange, which then have ripple effects out into the cardiovascular system. Physiologically, it's also really important to separate conceptually the acute versus chronic effects of air pollution. Acute effects happen quickly. They are typically significant reactions to a short duration exposure to a pollutant, and often one that is present in high or higher concentrations. For example, if you're in a room with high carbon monoxide concentrations, you quickly can lose the ability to transport oxygen, as carbon monoxide is carried across the capillary networks, deep in your lungs, and into your bloodstream. This is an acute reaction that can end in death because it interferes with the ability of your blood to carry oxygen to your muscles and other tissues. That's an acute reaction. But air pollution also has long-term or chronic effects. When you live someplace that is polluted, your lungs are always coping with the presence of pollutants that can impact physiological function. So over time, you can see declines in things like respiratory function. You can have the appearance of respiratory disease or even the appearance of cancers if you're being exposed to carcinogenic chemicals that are transmitted through your lungs into your bloodstream or other parts of your body. Lastly, these two can get mixed, and chronic long-term exposure to air pollution can make you more likely to experience acute reactions such as heart attacks when air pollution concentrations spike. When you see a warning that, say, sensitive groups should not be exercising outdoors because of air pollution issues, the concern is that poor air quality is going to exacerbate some existing medical problem and create an immediate acute need that has to get addressed, like a heart attack. The other way we understand the impacts of air pollution is through statistics, and this is really something that is critical to understand. The actual statistics that are used in epidemiological studies are beyond what we'd be able to cover here. But the basic idea with statistics is that you can ask a question such as, how many people would normally have died versus how many people died today after exposure to a pollutant? Or, how many heart attacks occur on an unpolluted day compared to a number on a polluted day? In both of these cases, we're looking at an unpleasant reality of human existence, and that is that people die or get sick every day. And on average, there will be a certain number of people that, for example, go to an emergency room each day for a heart attack. On the left side of this image, you see my poor illustration of 3 people going to an emergency room on an unpolluted day. If you can imagine many days like this, you can get a sense for what the background health access would look like in a community. We can then compare those numbers to the numbers we get on a polluted day, or a set of polluted days, and ask the question of whether more people are using health services on these types of days. In my simple illustration here, you see an extra person walking into the emergency room, and that would represent a 33% increase in emergency room use compared to the unpolluted circumstance. Statistics are really important here because otherwise we would not have any other way to understand the cumulative effects of air pollution on health. And so many air pollution studies use an approach something like this to try to untangle the natural causes of sickness and death with those that are linked to or exacerbated by air pollution. The statistic that is frequently used to represent the long-term effect of air pollution is called a disability-adjusted life year, or DALY. In effect, this is the number of years that are lost from an average lifetime due to the exposure to air pollution or some other environmental health issue. As in a prior example, the statistics are too intensive to go into here, but this calculation is used frequently in environmental health studies. This map that we're looking at is from a really interesting paper in 2020 where they calculated the cumulative effect of exposure to particulate matter and ozone around the world. And these numbers and the map should probably shock you. In the United States, for example, you would read this graph as saying that on average, the exposure to PM and ozone takes somewhere around 10 years off of an average lifetime. In other parts of the world, that number can increase to over 20 years. You're probably noticing the Eastern European and Russian numbers here, which are very high, and the paper doesn't explain the cause, but my guess is that it would have something to do with the high particulate pollution associated with coal combustion for home heating and electricity generation in this part of the world. At least that's my best guess. You can also see very high numbers for China and India that reflect the massive pollution problems both countries are facing as their economies have grown rapidly and the demand for energy and vehicles has increased rapidly in these areas. That's the big picture on physiology. So let's now take a couple of examples of actually what happens in your body when you're exposed to pollution. Particulate matter, and particularly particles below 2.5 microns in diameter, are a major source of health impacts due to air pollution exposure. When particulates move deep into your lungs, they create a lot of different problems. Some of those are listed here. So, for example, your body responds to inflammation triggered by particle exposure in a number of different ways that can cause harm. Thrombosis, or a form of clot formation, can be increased after exposure to particulate matter, and this increases the risks of clots that cause heart attacks or strokes. Your heart and circulatory system will respond to increased PM in a couple of different ways, including an increase in blood pressure due to how your blood vessels dilate or expand and how much volume your heart is pumping out at a particular point in time. This is one reason that heart attacks go up on high PM days in polluted settings. Like all the other pollutants, the impacts tend to be highest for people who are already vulnerable for some reason. For PM exposure, this includes asthma, diabetes, and people who have other respiratory forms of disease like COPD. Ozone is a secondary pollutant that is formed from the reaction of nitrogen oxides and volatile organic carbon compounds in the atmosphere. Lower atmospheric ozone is the same molecule that we find in the ozone layer in the stratosphere, but it has very different effects in the troposphere versus the upper atmosphere, and these two pools of ozone are distinct and separate. Ozone is a very reactive molecule, and one of those oxygens will break off quite easily and can cause a great deal of oxidative damage to tissues. Effectively, this ozone radical can tear apart organic molecules when it's exposed to this oxygen. So with ozone, we tend to see inflammation of lung tissues. We can see increased blood pressure, changes in heart rate, and possible mitochondrial damage. The mitochondria are the powerhouses of your body and produce the energy forms that your body needs to function. So it probably shouldn't be a big surprise that when ozone concentrations are high, we see more heart attacks and strokes. In our statistical example before, this would show up as more visits to the emergency room for these particular medical conditions when ozone concentrations are elevated. For one last example, I wanted to talk about lead because it has really different physiological effects than the other examples that we've looked at here. Lead is a toxin, and the impacts of lead exposure happen at the cellular level as lead interferes with key physiological processes such as the function of enzymes or the action of neurotransmitters. There are both acute and chronic impacts of lead exposure. And now that we no longer have lead in our gasoline in many parts of the world, the main sources are metal processing, some aircraft fuels, waste incineration, and some manufacturing processes. Lead is extremely toxic, and it remains a really important contaminant in many parts of the world. I will say in the United States, the phase out of leaded gasoline has had an enormous positive impact on the reduction of lead exposures. Hopefully these examples so far make sense, but here's where things get really complicated. This graph shows ozone concentrations in the Bay Area of California, and as you can see, things are slowly getting better, or at least were getting better until about 2000. The dashed green lines are the U.S. ozone standards, which have gotten progressively more strict over the years. These standards are based on studies that explicitly balance the health benefits from a stricter standard with the economic cost that that standard would bring to industry. This is a very difficult calculation to make, and inevitably, when setting an air pollution standard, the implicit question becomes how many deaths due to air pollution are acceptable in a society. The answer to that question depends on how a particular society values economic growth and the benefits it brings versus the preservation of health and the benefits that brings to society. And that's just the reality of how these types of standards come to be implemented. So there are always trade-offs between the cost of regulation versus the benefits that accrue from health protection. But as one last point in this video, I want to address the issue of these economic versus health impacts because many people think that they're very separate, and our choice with air pollution regulation is one of protecting the economy or protecting health. In fact, these two are linked because health impacts cost money in the form of medical treatment and in lost productivity within the economy, and these impacts are non-trivial. A recent study out of Stanford in the journal PNAS estimated the cost of PM air pollution in the U.S. at almost $800 billion per year, or about 5% of U.S. GDP. Multiple studies of national economic output show very large impacts of air pollution on reduced GDP, and due to these reasons of healthcare costs and lost productivity. And then collectively, when you look at the long-term impact of air pollution regulation in the United States, there is a net large economic benefit that accrues from protecting air quality because it reduces these costs, and those savings are manifest in other parts of economic productivity. To wrap up, we see that health impacts can be assessed from physiological studies and from statistical studies. The different forms of air pollution affect many different body systems, but usually start with the respiratory system. And lastly, air pollution has very large and measurable impacts on human lifetimes in every country on the planet, and it also has impacts on economic growth for many countries. And those economic impacts come both in the cost of regulation, but also in the savings and increased productivity that come from improved health outcomes.